Hi, this is Brian Fogarty, and this is a video for Chapter 14 for the book Quantitative Social Science Data with our second edition. So in this video, what we're going to do is take a relatively quick look at zero, inflated, and hurdle count models. So we would use these type of count models if we have a problem with excess zeros. So with our negative binomial model, we had checked and we saw that we did not have a problem with excess zeros, so we didn't need to go down this path. But I still wanted to cover this because it's a sort of important next step in terms of trying to figure out what is the best count model to use for our data. So let's do this. Let's check whether we have an excess zero problem with the Poisson regression model. Okay, so again, even if we have a lot of zeros in the data, that doesn't necessarily mean we have a problem with zeros if our regression model is adequately handling them. And by adequately handling them, we're talking about, does the model predict close to the number of observed zeros we actually see, right? So is the observed and predicted zeros close? So we're going to use the check zero inflation function that we used earlier. And here we're going to use or include our saved model, model.prm. Okay, so let's run that. Okay, so here's the results, right? So we see there's observed zeros 81, same as we saw with the negative binomial, predicted 24. So ratio 0.3. That's terrible. That's a terrible job. So it's only predicting 30% of the errors. And it also tells you here in red, model is underfitting zeros. I find it kind of funny because when with negative binomial the text was what was it, model seems okay, right? And it was predicting 96%. This should say like model is doing a terrible job. Model is seriously underfitting zeros. Okay, so if for some reason this was the model we chose, or let's imagine this was our negative binomial and we got a result like this, we would want to consider an alternative, a zero inflated, or a hurdle model. So in the text, I include and discuss information about these models. I'll try to kind of go through them a little bit here. The basic idea of both of them is trying to specifically model the zeros, with the idea that if we can model the zeros, then we'll do a better job with the positive counts. So hurdle models, what they do is they separate the process completely. So it uses a binary outcome model to predict whether a count is zero or not zero. Not zero being it's some positive number. And then for observations that are not zero, so at least one, a count of at least one, it runs a count model. And technically, because there's no zeros in that, these are considered zero truncated models, which just means you can have a zero. But with hurdle models, these are completely separate things. Okay, zero inflated models are a little bit more complicated in the sense that it treats zeros as being generated out of two possible processes. One is where an observation is always zero for some reason. The other is that an observation is 0 because it just hasn't had a positive count yet. But it's not the case that it's always going to be 0. So the zeroinflated models so it also uses a binary outcome, but when it models that, it's not it's not separate from the rest of it, or the count model part. It feeds that information into the count model part, so zeros are not excluded from the count model part. Both of these, so zeroinflated and hurdle, the count model parts, the sort of standard, are Poisson, so you'd be zeroinflated, Poisson regression, zeroinflated negative binomial regression, and then hurdle. Again, it's hurdle Poisson, but it's really the zero truncated, because that's what the model is. So which one do we use? To be honest, I think the guidance on this is pretty bad. Some researchers that specialize in count models suggest that you should really only use zeroinflated if you have sort of a real understanding of why of the zeros. So do you know why a variable might be 0, and you have predictors to really explain that? If you don't, then they advise using the hurdle. But it's also the case that some fields tend to use zeroinflated more than hurdle, and vice versa. The other problem that I've had with zeroinflated models is that the binary part of it is not always that clear. Like, there's not great guidance of what to include. I mean, that's true for the hurdle as well, but because the zeroinflated is combining these things, so it's like it's a mixture model, our choices about what predictors to put into the inflation part, into the binary part, really matter. So anyway, okay. So there's more in the chapter on this, but just realize we have a couple different options if we have a zero problem. All right, so let's actually check out running this stuff. So we are going to use a function called zeroinfl. I don't even know how to pronounce zeroinfl. So shortened inflation. Shortened inflation. That's what we need right now. This is from the package pscl. Okay, so it gives you a bunch of information here about like who created it. It's kind of interesting. Usually the packages don't have this, but here it does. So what we're going to do is we are going to run first a zeroinflated model. So I'm going to do summary, and I'm going to call this model.zip. All right, and then we're going to do zero infl, and then we are going to specify two parts of it. The first part is our count equation, and then the second part will be the inflation, which is, I keep saying inflation, it's the binary part. So we're going to do article cites. This is our outcome variable, and then tilde, and then tweetdom plus woman lead author plus full prof. Okay, so that is our count part of the equation. And then we're going to do this vertical line. And this vertical line separates the count and the inflation equation. So we don't need to re-specify the outcome variable, but we will include the predictors. So tweetdom plus woman lead author plus full prof, and then we specify the data, and that is data equals citations. So the default here is Poisson, so we don't need to specify that. Okay, so let's highlight this and run it. All right. So here is the results we get. They look, again, similar to, a lot of the regression outputs we've seen before. All right, so this top part, and it says too, count model coefficients. This top part is our count model. This bottom part here is our inflation equation or binary outcome model. Okay, so let's look at this first. All right, so this is predicting the probability of always being 0, this bottom one here. So we see that tweetdom is the only significant predictor. So if an article has been tweeted, then it's significantly less likely to always be 0. Okay? Up here, we have, we see tweetdom is also the only statistically significant predictor, but this is in reference to the count, the number of article citations. All right, so that's pretty straightforward. Now, there is a common test for comparing a zero-inflated model and a standard count model. So we can compare this model here, the zero-inflated Poisson, with the sort of quote-unquote regular Poisson. You can only compare sort of within the same family. So you can compare a zero-inflated negative binomial and a negative binomial, but you can't compare with this test that we're about to do a zero-inflated negative binomial and say a Poisson model. So that they can't cross over. Sounds like some horror movie or something like that. So this test is called the Vuong test. There's some issues with this test because it can be vague. It's very kind of temperamental. Some people don't like it. But it's very common. So it's very commonly used. So let's take a look at it. Okay, so the Vuong model is a likelihood ratio test where the null hypothesis is that both the zero-inflated and the standard count model are sort of equally close to the actual model, where you don't know what the actual model really is. The alternative hypothesis is that one of them is better. So the Vuong test has a test statistic based on a asymptotically normal distribution, and so it's all right. This is kind of weird, but the test statistic, if it's greater than 1.96, then the first model specified in the test is preferred over the second. If it's less than, less than negative 1.96, then the second model is preferred over the first model specified. If it's in between negative 1.96 and 1.96, then the models are indistinguishable. All right, that's all in the text because that's kind of hard to keep track of. All right, let's run the test. So it's the function is Vuong. Oh, yeah, Vuong, and we're going to do model.prm and then model.zip. Let's highlight that and run that. Okay, so we see that we have 3 versions of it here. The raw, AIC corrected, BIC corrected. So these corrected versions exist because the Vuong test is biased in favor of the zero-inflated model. So there has been corrections offered up to try to do a better job here. All right, so here's the Vuong Z statistic. This is the test statistic. So we see that all of them are 4 point something. So given that, we can conclude that the zero-inflated Poisson is preferred over the standard Poisson. All right. Now, let's take a look at the hurdle model. So we could actually estimate the hurdle model literally in 2 steps, where we run a logit or probit, where we have our outcome variable is where we create a new outcome variable where it's 0 if it's 0 and it's 1 if it's 1 or greater. And then we would run a second one where we filter out all the zeros and just run it on positive counts with the zero truncated Poisson or negative binomial. But we can actually use there is already actually a hurdle function that does it for us. So we're just going to use that. I'm just going to steal the code from the zip. All right, we're going to do model. I'm going to change this to HP. And then this, we're going to change the function here. Instead of zeroinfl, we're going to do hurdle. Okay, the rest of it is the exact same. Okay, let's highlight that and run that. Okay, so what do we see? The bottom part here, we see that this is the binary, all right, the binary outcome, and then this is the count model part. So again, tweetdum is the only significant variable here. But if you remember, in the zero inflated one, this sign was negative. The difference here is that what is being predicted is the probability of having a positive count. Okay, in the zero inflated, it was the probability of always being 0. So having a positive coefficient implies that if an article was tweeted, then it has a higher probability of having a positive count. Okay, and then up here in the count model part, we see that tweetdum is also the only statistically significant predictor. Okay, the last thing that we'll do here is we'll try to figure out which model is the best model to use. Okay, so we have our Poisson regression model, which I've bashed a lot in the chapter and also in these videos. And we just done the Vuong test, and the Vuong test says that the zero inflated is preferred. One way that we can compare models that are very different from one another, we can't use kind of standard statistical tests to do it, like likelihood ratio tests. We can compare AIC, BIC values. So let's look at the AIC. We are going to, let's look at all of these together. First, we'll look at the AIC of the ZIP model, the zero inflated Poisson. Okay, so 1541. Again, on its own, it literally means nothing. Now, let's look at the hurdle model. Almost the same. Okay, so at least now we have a second one we can compare it. They're essentially the same. There's really no difference between them. The Poisson model actually has the AIC saved as an object, so we don't need to use the AIC function. I'm going to do that. Okay, so AIC, when we compare them, the preferred model is the one with the smallest AIC. So we see that the Poisson regression model is much bigger than both the zero-inflated and hurdle. Lastly, let's look at the negative binomial. So we have model.nbrm and then AIC. Okay, so that's 1359. So looking at all of these, and I'm sure we could do a nicer job of kind of putting these together, but we see the negative binomial is 1359. So comparing these four models and just using AIC, we can conclude that the negative binomial is preferred. So I think we're pretty good on kind of diagnosing which model is the best one here. All right, so that is the end of this video. The next one, we're going to briefly look at interpreting zero-inflated and hurdle models, the coefficients. So thanks for watching, and I'll see you next time.